Hello, check. 100% fine.
हेलो, हेलो, हेलो। तू बोल।
Hello.
I think it's great. I so next, I think setup has been done.
hello, 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 hello.
Hello. Hello.
It's still on, and अच्छा हाँ नहीं ऐसा करो आप वापस प्ले पे हेलो
Hello, can you hear me?
This.
Quite close bar at the top. Yeah, I'll just put it at the bottom then.
It won't show anyway, right? When you go.
In, it will unfortunately. How does it work? I just close that window. It has so 3-4 windows I get for Teams, and I just close that particular window. I'll just I put it at the bottom.
All right. I think so.
No, it's still on.
I'm not supposed to have it on?
No, right now if you don't want to, but yeah, you can.
Yeah. I have no secrets. All right. So this thing will stay. Put it there. Faster for me to do this. Should I be using this or just this one? Yeah, sure.
This you don't have to use.
All right. I think we're good to go. Oh, my. Go ahead. Where? A bottle of water. Oh, this one. No, no, I mean, I've
Oh,
just
sorry,
opened
yours.
one. Yeah. Test, test.
Test.
अच्छा
Quando uno dice
Oh. No, questi
il nome della
sono
cattedra, sì,
della
sì, sì, sì,
cattedra.
lo so, ma a uno.
Quelli è il name chair.
No,
Quello, il benefattore.
sì, sì.
Forse sì,
Questo, sì.
non credo. È possibile che sia.
Okay, so welcome everybody to the first session for today. Okay, it's my huge pleasure to introduce the third invited speaker, who is Cesare Tinelli from the University of Iowa, USA. Uh, well, Cesare received his PhD at the University of Illinois, Urbana-Champaign in 1999. Well, I've been knowing Cesare for a long time, actually, and he's very, very well known in scientists in the community of SMT and more generally in automated reasoning and formal verification, where he has published more than 130 journal and conference papers in top revenues of the field. He also is extremely good in raising funds, okay, as we probably know. And this is a very good news for the automated reasoning formal verification and the S7D community. One of the one of the important feature of Cesare, that he has developed a lot for a big effort in services to the community. In particular, I can say he's the mastermind behind the SMT-Lib initiative. I believe that most of you know it. It's a worldwide international initiative to collect large amounts of benchmark problems in SMT, and in particular to regulate the standards of language and update it. And this is a really big effort, and sometimes I would say also very boring, but this something of huge impact and use in the community. Well, he's also coordinator and has helped developing many automated reasoning and formal verification tools. In particular, he's one of the co-leader of the CVTC 345 tool, which we all well known. And also he coordinates the StarXSec initiative, which is this large web-based platform where we can run our experiments, our tests, and also most of our competitions. Cesare has received many awards for both his scientific and his service work. He has received the NS Career Award, the Haifa Verification Conference Award for his service, and also he's co-recipient of the CAV Award for pioneering work on satisfiability model theories. He has been invited speaker of several conferences. He's in the steering committee of many conferences. He has been the chair of CADE, FROCOS, and TACAS. So you see both automated reasoning and formal verification conferences. He's in the steering committee of many conferences, and he's associate editor of Journal Automated Reasoning. He has also worked with lots of companies well, we all know that CVC 3, 4, 5 are widely used in many applications, in many industrial applications. So I could go ahead for a while, but I think that you are not interested in hearing me, but you are interested in hearing Cesare. So please, Cesare.
Thank you. Thank you very much, Roberto. We do go way back. Roberto was one of the first researchers I met at a conference as a student. So I would like to start, of course, by thanking the SAP Program Committee for the invitation. It's been a pleasure to be here. It's a pleasure to give you this talk. I also like to thank the local organizers for the wonderful hospitality. They've been fantastic. And then I'd like to acknowledge the funding, as Roberto was saying, that we have received from a number of sources, including Amazon Web Services, DARPA, NSF, and the Stanford Center for AR. The work I'll tell you about today is about proofs and specifically proofs in CVC5. And it's a major effort that spanned the last 4 years and involved the universities that you see here. These are all places that collaborate one way or another on the development of CVC5. I've singled out the people in red, Haniel Barbosa and Andrew Reynolds, because these are really the main engines behind the proof effort in CVC5 that I will tell you about. Notice not all these people have been involved in actual implementation work in CVC5. There's a lot of work that goes around it or outside the solver, so as I will explain as we go. All right, so I think for this audience, I don't really need to justify the fact that automated reasoning is being used extensively and it continues to be used in formal method applications. All one way or another rely on automated reasoning tools, and here, I mean everything based on deduction from set solver all the way to interactive theorem provers. I will focus on set solver because this is what we do. And I will tell you, what motivated our work, which is something that, again, in this community seems to be well understood, has been understood for a while. But whatever issues are in the SEC community and the SMT community are harder for a number of reasons. How many people are familiar with SMT solvers? Raise your hand. All right, so you probably know that the SMT solvers work a lot like set solvers, except that they deal with constraints, first order constraints, where you have not just propositional variables, but also terms that you relate in predicates. And all these constraints are over a number of theories. And where specialized decision procedure or other kind of mechanisms are used to reason over these theories. For this reason, they have very large code bases. So CVC5 is 300K in C++. So despite the efforts that teams put in making sure that these tools are correct, bugs remain. In fact, every year at SMT-Comp, the annual competition of solvers, you end up having solvers disagreeing on some benchmark, right? Which of course means one of them is buggy. And also a lot of people that do fuzzing have a great time finding bugs in SMT solvers. But SMT solvers are the engines that a lot of these applications and formal methods are based on. So how do you deal with this? The fact that you can't trust the solvers as they are. Well, you could think about certifying them. That is, for instance, proving formally they're. But this is just too costly. These are, again, humongous systems. There have been attempts to verify simpler versions of these systems, but these are usually not as well, full features as the regular solvers, and they are also relatively slow. But there's also the problem that once you certify or qualify, depending on the kind of process you go through, once you qualify a tool, it's really hard to develop it further because recertification or requalification process takes a long time. So this tends to freeze the tools. It's definitely the case in industry. In academia, we would like to go on developing them because there's still a lot of research that we can do with them. And so the alternative, which once again, I don't need to really explain that much to this audience, is that of having a tool that produces proof certificates. And so it produces some artifact that describes a proof of, say, unsatisfiabilities for refutation-based tools like Satisfiability solver that can be checked independently by a trusted third-party small checker. And if this is done properly, also relatively fast with respect to solving time. And so the important point is that the confidence of the result is decoupled from the correctness of the tool. You don't need to trust the tool, you need to just verify the results that it gives you by looking at the certificate. But it turns out that producing certificates in SMT is not nearly as common as it is in SET. So why is that the case? Well, the problem essentially is due to the complexity that I mentioned earlier. There have been attempts of collecting and storing proofs efficiently in SMT solvers while they're solving. But there's really no established methods for doing this because it depends a lot on the theories that the solver supports and the kind of reasoning that the solver does, which, again, depending on the theories, might be quite different. So there have been many attempts, there's no solution that works for all. SMT solvers do a lot of sophisticated processing of their using rewrite. I've lost the mic. Back. So they use a lot of rewriting techniques. So which makes it complicated. So there is substantial initial progress on this, but we still have a lot of challenges. In some cases, SMT solvers use techniques for which we don't even know how to produce a proof. For instance, for nonlinear arithmetic, we use cylindrical algebra decompositions, and we just don't know how to generate proofs for that. Or regular expressions, when in case of solvers, they solve constraints of a regular expression and strings using automata-based methods. Generating a proof is also hard. The issue of standards is also an important one. It's been relatively difficult to establish a standard, input-output standards for SMT. I mean, this is something we've done over the course of 20 years. We're really not at the point of establishing the standards for proofs in SMT. We're not even close. There is a couple of attempts, but not much success. And the reason is, again, different solvers do it differently. They use different proof systems, and we're not there yet as a community. And also doing scalable and trustworthy checking of proofs is also a challenge because SMT solvers generate complex proofs. Complex both in terms of size, it is very large, in terms of the kind of checking that needs to be done. Traditionally, SMT solvers they are certifying, don't actually produce full proofs in technical sense, but they produce witnesses or proof sketches that then need to be elaborated a lot further. That is, some of these proof sketches require actually search to check the proof, right? So it's expensive. So we set up our goal. This is another one. All right, try this one. So in the developers team of CVCV5, we decided that, can you hear me? Is it okay? Sorry. That we like to address these challenges head on and started with the following goals for our tool. First and foremost, being certifying, but while minimizing the impact of proof production in the solver's behavior and performance. Often when you add proof production facilities to a tool, you really modify the way the tool works, and then you can have degradations in performance. Generating the proof itself requires effort, and that, again, you pay when you solve it. So our goal was to maintain good performance, maintain all the relevant, optimizations that the solvers use to improve their performance, even when we are in production mode, and achieve a acceptable overhead for proof checking. So these are quite difficult goals, and you need to find the right balance, between, again, performance of the solver and acceptability of proofs, the proof overhead. But we also decided that, so if we're going to do this, we're going to do a properly, in our opinion, which is we decided to build an internal proof checker in CVC5 that for every proof rule application. So when it is in pre-production mode, CVC5 will identify the proof rule that was used to come up with a conclusion and check that the application of that rule is actually correct. So what that means is that, when in pre-production mode, there's a lot of checking going on within the solver itself. Also, our goal was to develop a modular infrastructure that allows you to do fine error localization. That is, if you do discover that there is a problem in reasoning, we do want to fix it, but we don't want that you have to wait until some external tools discovers that one of our proofs is incorrect. We want to do it on the fly as, again, we are generating proofs and doing things like, for instance, checking every single proof rule allows you to identify in which part of the systems are responsible for the bug and try to fix it. But for performance reasons, we're also quite interested in what we fix as well, the possibility of customizing proof generation at this level of effort and so cost. Okay, so, and here the balance is between low effort and more sketchy proof versus full effort and fully detailed proof. Finally, we wanted to support different formats because this would allow us to leverage different proof checkers. So lots of these goals, as you see, might be are in opposition to each other. So the challenge was to find the right balance. And so we'll tell you about our efforts of what we've done to achieve these goals, which by and large have been achieved. The proof production work in the CVC5 team is still ongoing, but we have reached very important milestones that, for instance, allow our industrial users to check proofs in production, and allows them to work this at the industrial level, so the level of millions of proofs a day. All right, so this is what I will tell you about proof generation in CVC5. I'll tell you about a new proof framework that we have developed to support this effort, and then I'll show you, time permitting, some initial experimental results. All right. Something froze. One sec. So roughly speaking, this is how modern SMT solvers work. They're based on CDCL, the CDCL framework, like set solvers, but they deal with theory reasoning. That is, they reason about predicates, again, that are over a theory, and they contain operators and selected operators in these theories. But this is quite illustrative and representative of what happens in most SMT solvers. The formula, a simple formula is taken in typically in SMT-lib format, then it's pre-processed and classified. That is, we first simplify the formula globally using essentially rewrite rules that are based on the base logic of SMT, which is many sorted first order logic. These will be examples of rewrites that are done at that stage. And then the formula, which is an arbitrary formula in many sorted first order logic, is classified, turned into class form. And then the Boolean abstraction of that formula is fed to a standard set solver for Boolean reasoning. Okay. The set solver gets that Boolean abstraction and tries to make it true by essentially deciding which of the predicates should be given value true or false. But this, at the level of the initial formula, is a conjunction of predicates in a theory or in a combined theory. And so theory solvers are used to reason about this set of asserted literals coming from the set solver to make sure that the conjunction of all these literals is consistent in the theory. If more theories are involved, the theories reason modularly about parts of the formula or parts of the set of assertions coming from the set solver. But the net result is that the combination of the theory then decides whether that conjunction of literals that represents, again, a Boolean satisfying assignment for the Boolean skeleton, to check whether that conjunction is consistent in the theory or not. If it is, you're done. You've actually proven that the formula is satisfiable. Otherwise, you need to try another assignment, and this is forced by having theory solvers return lemmas, that is, new clauses, to the set solver that forces the set solver to continue the search. Locking clauses, essentially. So theory solvers check the consistency of sets of literals, but also produce lemmas, and internally they do all sorts of elaborations of the formulas based, again, on deductive techniques, and that includes also a lot of simplification. So theory solvers usually also have a theory rewriter inside that simplifies the literals they have to work with. These rewrites are theory specific and also context dependent. They depend on a set of assertions that have been entered until then in the theory solver. So these, at the bottom, you will see examples of simplifications that are applied, which are theory specific. So what happens if you want the solver to generate proofs? Then, well, you need to build a proof infrastructure. And this is a typical way of doing this. I mean, that's specifically the way CVC5 does it. So what do we do? As you see here, the stuff in violet. First of all, we generate a proof sketch that is essentially the resolution proof provided by the set solver in case the system has discovered that the input formula is unsatisfied. Because of the communication that I mentioned earlier, or the collaboration between the set solver and the SMT solver, the inconsistency is always discovered at the level of the set solver because all the assignments that the set solver tried have been rejected by the theory. And the rejection has been forced by the addition of a theory lemma that is, something that is valid. So what that means is the set solver at that point recognizes there are no more alternatives, hence the system concludes the formula is unsatisfiable. The set solver can produce a proof that is a purely Boolean proof about the inconsistency of the input clauses and together with the lemmas that come from the theory solvers. Okay? And so at that level, at the Boolean level, the proof is simply a standard resolution proof where the leaves are either input clauses, I should say, or lemmas generated by the theory solvers. Then the proof can be specialized further by providing now a proof in the theory in question for every lemma that has been added to the set solver. Again, lemmas are valid statements in the theory, and so they can be proven. So the full proof is, this sort of combination that I mentioned. So examples of lemmas here would be these ones. For instance, this is a lemma that captures the congruence of about the symbol F, and the other is a lemma that captures transitivity of the less than symbol and the theory belongs to. And so what we have in CVC5, we have first of all, a pre-processing step generator that will generate a proof of correctness of the translation from the input formula in the arbitrary SMT-lib format to the set of clauses that are actually processed by the solver. Right? So this step needs to be proven correct, and so there is a proof of essentially of equivalence between the input formula and the generated clause set. Every lemma, as I said, that is generated by or produced by a theory solver comes then with its own proof, but we don't actually generate the proof as we're solving. We generate essentially a generator for a proof for each lemma. then later on, a post-processing step we can call to finally produce a general proof. And so what happens is during solving, there's a lot of logging, a lot of creation of generators for proofs for lemmas. And then essentially this is done internally in SMT, in the SMT solver. But then only at the end, if a proof is requested, the full proof is assembled together. So only at that point, the pieces are taken, put together, and the various lemmas are provided a proof. So this is essentially, it's done in a lazy way to minimize the amount of time that it takes to generate a proof while you're solving. Right? You don't want to slow down solving. The proof that is generated at this stage, that is in this post-processing phase, it's also a proof that is not as detailed that it could be, because, for instance, it contains applications of a lot of derived rules in CVC5. So CVC5 is a basic set of derivation rules or proof rules that it uses to justify its reasoning, but it also has a number of what you could understand as macro rules. Okay, so the first approximation of the proof you could understand is just the Boolean skeleton without the proof of the Boolean skeleton of the formula, without proofs of the theory lemmas. Then a second level approximation is you have the proofs of the lemmas, and then possibly using macro rules. And finally, you have a proof that where all the macro rules have been expanded, like in this example here. So the rules on the left is in fact standing for a subtree that uses now basic rules. Once this is done, then the proof can be converted into a specific proof format. And that is done first internally by translating the proof in the internal AST into an AST that is specific of the target format, and then using a pretty printer that produces the proof textually in whatever format we are supporting. We support more than one format. Notice that there's no internal proof checking once that format is generated, because again, the idea is that the proof will be printed and some external tool will check the proof. So just to summarize, this is essentially what a proof from CVC5 looks like. That is, those are the various components, and this is the way the proof is structured. There is, again, this is the set proof for the sketch or the Boolean abstraction of the formula. And then there are the various proofs of the conversion to CNF, the various lemmas, the rewritings that are done at the very beginning globally on the formula, and any other kind of pre-processing that occurs in there. So rules in CVC5 really have this form. That is, they have the form of having a set of premises and a conclusion, and also a set of terms that we call arguments. These are basically information that is needed to generate the proof, to generate the conclusion. We have about 160 proof rules in internal calculus, and these are all documented on the CVC5 website. So if you go there, you will see that. See, these are all examples of various rules. Substitution, macro rewrite, evaluation, and then rules that are more specific to the various theories and so on. Each of these rules is implemented somewhere in the piece of code. The reasoning that is represented by these rules is implemented in CVC5. All right. Now, one thing that SMT solvers do a lot more than SAT solver is a lot of rewriting. That is, a lot of reasoning is done by the deduction steps exemplified by the proof rules, but the formulas are massaged continuously with rewriting. So how do you account for that? Because you do a lot of rewriting, you need to explain why this formula that appears in the proof is become all of a sudden this other formula. So how do we do that? Well, because the rewriter in CVC5 is rather complex, it's been difficult to actually make it proof-reducing in the sense of justifying all the rewrites that it contains. So what we've done is something that is, post hoc, where we, to count for all the rewrites in CVC5, we have developed a language for describing rewrite rules, again, for the needs of SMT solvers. And then, well, an example of such a rewrite would be this one. And then use these rewrite rules essentially as a specification to generate, to fill in the details in a proof to justify why a formula has been converted from one format to another. So as an example of a rewrite rule, this is a rule that operates over strings. It takes as input these terms here. That is, the rule is parameterized by string terms P, S1, S2, which actually stands for 0 more terms, T1, and then T2, also standing for 0 more terms. And the rule, you can read it as having a left-hand side and the right-hand side here, that essentially saying if you have two strings, two concatenation of strings that share a prefix, P in this case, then the equality of these two strings can be reduced to the equalities of the corresponding suffixes. Okay, so this is a simplification rule that the string solvers in CVC5 has, and this rule captures one of those simplifications. Okay? We have about 400 rules to do this. The largest set of rules is definitely the rules in the theory of strings. First of all, because it's a complex theory to reason about, but also because it's a theory that one of our funders, Amazon, really cared about in their applications. And they wanted to have proofs for that. So what we've done is we've implemented an automated elaborator that takes a proof with no justification or rewrite steps. And other than saying, well, this formula has been rewritten to this other formula. So this is essentially the proof rule that is used to justify a rewrite. And then looks into this database of rules, again, specified declaratively, and tries to figure out how to justify the rewrite step about one of those rules. So this process is fully automated. That is, the specification of the set of rules, as you see here in textual form in the Raider language, is done manually by us. But then these rules are compiled, and in a proof elaboration time, every rewrite step indicated in the proof generated by CVC5 is replaced by the actual rewrite automatically by doing matching operations on this database of rules. So this has been extremely important to enable the generation of fully detailed proofs. Our proofs in CVC5 can be derived so that they have no holes at all. Okay, there's nothing that you need to do in a checker other than simply verifying that the premises matches the conclusion given a rule application. Because we do, yes. Yes, it is expensive, and that's why we have several levels of proof. I got the several levels of details. Okay, so the default proof that is generated has a bunch of holes. So for instance, it uses macro rules. It doesn't justify any of the rewrites that are done. But then there are several levels of granularity, as you see here, that where you can ask the SMT solver for more and more detailed proofs, if you're willing to pay for, the cost that it takes to do this. Of course, the downside of this is that if you quickly get a proof that is at a higher level of granularity, then you need a smarter checker to be able to fill in the holes, right? Whereas at the lowest level of granularity, then you need a dump checker.
And the way I understood was that you simplify these, you express these rewrites in terms of some other rules that yes, you make up, nah? But what is the guarantee that those other rules are correct?
This is a good question, and it doesn't apply just to the rewrite rules. It also applies to every derivation rule
yes,
that is in the proof. So the guarantee of correctness here cannot be internal to the system. A meta argument is needed. And so what we've done is to formalize these proofs in an interactive theorem prover, these proof rules in interactive theorem provers, and prove their correctness in there. part of the reason why this is a massive effort is because there's a lot of time, we need a lot of time to do this. And a lot of the people that I listed on the third slides have been working actually on this. So for instance, doing a formalization in Isabelle, we have one in Lean of the entire proof system of CBC5. We have not completed this, but our goal is to do that. Now, the proofs are simple enough that, and they are documented. And so again, you can inspect it and see whether they are correct or not. But again, we're doing this formally into an interactive theorem proof. All right. So this is the full architecture here that involves proof generation. So now the key question is, which format do we use, given that a number of formats are potentially available? Notice that the way we've done this in such a way that you could choose the proof format at the end, essentially. And all you have to do is to add a proof converter and a 3D printer for the proof. And that you don't have to modify anything else in the rest of the system. So there's been previous work on proof format for SMT, specifically a language called ALET, which is the evolution of a proof language that was introduced by the Verity SMT solver. It's based on SMT-lib syntax. SMT-lib syntax, for those who are not familiar with it, it's basically an expression-based syntax. Lots of parentheses, everything is in fixed form. The proofs themselves are natural deduction style. That is, you start with assumptions, and then you have all the conclusions of various applications of rules until you generate you derive the empty clause, because all of our proofs are refutation proofs. So that's the same also for the ALET format. There are checkers for ALET, or at least fragments of it, in Coq and Isabelle Hall. So in other words, you can produce the proof, and then you can check it using a Coq plugin called SMT Coq that will tell you whether the proof is correct or not. Or you could give it to Isabelle, and Isabelle will do something similar. But the performance, of these checkers is really not all that great. I mean, the performance of this approach, that is using an interactive theorem prover to check a proof generated by an SMT solver, is not really a viable one, because it only works for relatively small proofs. And so there's a need to develop specialized proof checkers, which has been done here in the proof checker Karkar that is developed by some of our, it's a group of the CBC5 group. Okay, so this is an efficient standalone checker for ALET. But ALET as a language has a number of shortcomings. The proof rules are specified informally on paper, going back to the previous question. So they're documented in a PDF. They're available only for a limited number of theories, and it's time-consuming and error-prone to extend the rules. Also, they currently do not actually capture the entirety of CBC5's type system and proof calculus. Okay. Another approach based on previous work, which we did at Iowa and then introduced into CBC5, was based on DLF, the Edinburgh Logical Framework. So this is a logical framework that was designed a while back in the context of, or in the programming language community, that would facilitate the formal specifications of other languages. Okay, so we have taken essentially LF and extended it with some conditions, which is essentially small trusted programs that you can use to make your rule more powerful and hence your proof more compact. And basically, we added at the end a framework and a tool where a proof system for a specific prover is user specified. Okay, so the way you should understand this is we developed a generic checker for LFSC. It takes an input, not just a proof, but also this formal description of the proof system, and tells you whether the proof is correct with respect to the proof system. In fact, the proof system can be precompiled. And so this will be analogous to, the YAC in compilers, where you get the specification of the grammar and you generate a parser. We get the specification of the proof system and we generate a checker for that proof system. This has been quite successful, but the approach had a number of shortcomings. First of all, the performance of the original checker was great at the time when, this is already 15 years ago when we started, but now the checker was not performance enough. But also, perhaps more importantly, the proofs are at a level which is too low. Proofs are essentially big terms that you need to check in the checker by turning proof checking into type checking. And so it's very good for the tool, but the human really cannot really understand what the proof is saying. That's a very good point. And this is what we said initially. You know, why do we care? This is a format. Yes. But as you're developing these tools, you want to debug them. And you don't have terabyte long proofs. You know, you have small proofs. And only if you cannot even read those, it's very hard to develop. And so we moved towards proofs that are still not, you know, they're still, well, first of all, format. We moved to proof formats. They are still formal, but more legible to the human users, as I will show you in a moment. And there was limited tooling support for LFSC. So we decided, oh, by the way, there are other professors. Obviously, everybody here knows about the professors in this community that led to the standards DRAT and LETRAT. And, you know, which is great, but it's not enough for SMT because you can only reason at propositional level. You know, we need to reason at the first order level. There are some extensions of DRAT that in the direction of first order theory. This is very preliminary work being done at Amazon by Bruno Duterte, and they don't handle all the complexity of reasoning in an SMT solver. And then I mentioned, you know, the alternative of developing a proof checker in an interactive theorem prover directly. There's also been efforts to do this in Lean as well. But well, first of all, it requires substantially more effort to develop a proof checker within an interactive theorem prover, and it's usually slower. Although, you know, the way Lean is going, hopefully this is going to be actually something that is viable. So what did we do? We developed a new format based on the experience that we had until now, both internal and external experience. And the main features of this format is the flexibility of LFSC. That is, you can have user-defined proof systems, but it uses the syntax of ALET, which is similar to SMT-lib, and specifically to SMT-lib 3, an upcoming new version of SMT-lib that extends the logic from many first-order logic to a high-order dependently typed logic, which is a lot more useful in many ways. So we wanted also the fine-grain, the level of fine-grain proofs that CVC5 supports. So, you know, at the level of array rules. And at the same time, enable the generation of efficient checkers, which we've been doing in a number of ways, including using direct technology, as I will mention later. And so the goals were a clear formal definition of CVC5's proof calculus, a baseline checker that is called ethos, and the framework that you get is a framework for intermediate proof languages, which is generic. Because the framework is quite powerful, you can specify not just the proof system of CVC5, but the proof system essentially of all SMT solvers, and in fact, even more than SMT solvers. And again, you know, the goal is to have flexible and efficient verified checking of proofs in SMT in general, not just CVC5. So I will tell you about the language by showing some of the features and actual expressions in the language. This is concrete syntax on the right here. So we have the language is command-based like SMT-lib. A proof is essentially a script. That is a list of commands, and you have commands to define the symbols involved, the theory signature, right? So that command there is defining the first one, the Boolean and then the Boolean implication. It says examples. Then we have a command to define proof rules, and these are along the lines of what I showed you earlier. That is, you can define, well, parameters, premises, the arguments, and then a conclusion of the proof rule using that syntax there. And because we can have side conditions that operate on the proof rules, these side conditions can be specified in essentially a mini programming language that is included in the framework here. So this is an example of this end function that is used in the end elimination rule to extract the ith conjunct for conjunction of formulas and infer that one. A proof itself is a sequence of commands of the ones that you see here. assumptions about the assumptions of the proof, and then derivation steps. So a step here says we derive a conclusion P2, which is B, by applying the rule and elimination to the premise P0 and using as an argument 1. That means we want the second conjunct in the conjunction. And this other step here will say that there's a new step, P3 derives D by modus ponens from these premises, and so on. So consider a problem in SMT-lib format. So this is something that you can give to an SMT solver that supports SMT-lib, where you define a number of symbols, make some assertions over them, and then you want to check whether the set of assertions is satisfiable or not. So what do you get if you use CVC5 to do that? So again, this is the input. You can give that to CVC5. And when in proof production mode, then CVC5 will produce a proof in the syntax that I've just described. It looks like this. Now, I think you would agree with me that this is a fairly legible proof because it is small, but declarations are constants. Some macros symbols are introduced, the assumptions that were in the input file, and then the rules. But notice that the proof is actually a sketch. It has a number of holes here. That is, there is some simplification of this formula that is not true to false, which is unjustified. We just said by rewriting, okay? And similarly for the other one. If you want a full proof, fully detailed proof, then CVC5 will produce it and fill in those holes. That is, justify all the holes that Ed said, for instance, I said by rewriting, by telling you exactly which sequence of rewrites have been applied to go from the left-hand side to the right-hand side of the proof in the sketch here. Now, the format, as you see, is really similar to the LF format. You know, if you look at it, they seem like they are the same. There are technical differences between them, but that was on purpose. You know, the way Alet defined the format seemed, you know, something that would be useful to have, and so we adopted that in the new language, you know, yeah. And here's the proof in LFSC. So Moshe, check this proof for me, please.
I'm a proof generator.
Very good. Suppose I need to debug this. Not easy. Okay. So this is what LFSC would do. Essentially, this is a term with holes that can be filled in automatically that needs to be checked for correctness. Essentially here, the checker will verify that this term is well typed, where the type of the term is the formula that you want to prove. Okay, so this is based on basically the way most interactive Turing provers work, that they turn deduction into type checking. All right, so this just should give you a basic idea. But when you produce proofs for real, you need to worry about a lot of our issues and are not so technical, but they're also important. So for example, suppose you're given this problem, you give this problem to CVC5, and then you get this proof certificate. And you check it, and it goes through. What can you say about the original problem? Really nothing, because you don't know that that proof is a proof of your input. It could be just a valid proof of something, right? So you also have an additional obligation to check that the proof you got is indeed a proof of the input problem, right? And so how do you do this? So you know it is possible by basically adding in the proof a reference to the input problem. So specifically here, we can refer to the input problem file. And notice that once we do that, we remove from the proof all the definitions of the various symbols that are used in the problem. But we do use those in the proof. So this gives you the guarantee that if you give this, again, to the checker together with a reference, then it will extract the right information, that is the right premises, from the input file, and then generate the proof. Now, Ethos has among many features. That is our proof checker for Unoya, and one of them is the support for Oracle functions. Okay, so basically, you can use in the checker Ethos external function that you call as oracles. So this makes the framework extensible. Okay, if you have oracles you can trust, then you can plug them in. And communication is via text in SMTlib 2 or 3 format. So these would be examples of oracles. You can define an oracle that checks whether, I don't know, a number is prime, or some oracle that computes some real functions over arguments, or one that processes some subproof. Okay? So all of this is introduced for practicality. And obviously, what you need to do in that case also to have arguments that say, well, if the external oracle is correct, then what I get is a legitimate proof. Why is this interesting? Because this is how we incorporate DREP proofs in Ethos. Okay, they are oracles. So what you can do right now is in CVC5 use or generate a proof that remember I told you the proof is there's a Boolean proof and then there's a theory proof, where the Boolean proof actually is in DREF format and the rest is in the standard form. And then use a DREF proof checker, and specifically we use DREF trim to check the Boolean part. Obviously, you also need a little bit more. You need a little checker that checks that the DIMAX proof generated by CVC5 really corresponds to the Boolean proof. Okay, so but this is a relatively small program, as you see here. So this allows us to generate proofs that can be either fully checked by Ethos by writing them fully in the format that I show you, or when the Boolean part is big, by providing the Boolean part in DREF format, and then have Ethos use DREF trim as a sub-procedure to check the Boolean skeleton. But this requires, first and foremost, to formalize the proof system. Remember, the proof system is user-defined. So we've done that. We have specified, about 115 rules that CVC5 uses, all the common ones. And this is about 4,000 lines of Unoya specs, which again, you can inspect and prove in some other proof checkers separately. So in some other theorem provers separately. So the formalization that I'm talking about includes the complete definitions of all the theory symbols that CVC5 supports, including the type system, and the formalization also of Scholar internal symbol. This is a technical thing I will not talk about much. And all the proof rules for classification, resolution, or depth proofs, and finally all the proof rules for theory reasonings over a large set of theories that are supported in CVC5. Ethos is the proof checker, as I mentioned, is relatively small and highly efficient. So it has, that size, and it incorporates, all the things that are needed to actually check the proofs. These are the key features there supporting Unoya. All the features basically I've described. So the key features of Unoya, they're supported in the Ethos checker. We also do signature compilation C++. That is, you can take the entire signature, compile it to C++ so that proof checking is faster later on, because all the proofs now become built-in, all the proof rules. We've been, among other things, we've been testing this proof checker on a large set of proofs that we have generated from SMTlib, but also on 4.5 million, that's not a type, 4.5 million proofs generated by Amazon internally. So this has been extensively tested. And it's documented and available at that URL. So what are we still doing? Are we done? We're definitely not done. There's a lot of ongoing work. And the work involves the fine-grained reconstruction of the 3 steps, as I mentioned earlier. Because there's lots of rewrite rules, we need to formalize them in RARE. Then we had to develop this framework that automatically matches rules to what CVC5 actually does, and the elaboration of complex rewrite steps have to be done every time you have a new rule that is a macro rule. I talked about the incorporation of DREP proofs. This is still ongoing because we want to make sure we do this very efficiently. The proofs generated by CVC5, so the proof produced by CVC5 can be generated in its internal format that we call CPC, which is essentially this instantiation of UNOIA with the CVC5 proof checker, proof system. But we also produce proofs in ALET and also visualize them in DOT. Now, the ALET proofs are currently used for proof reconstructions in Isabelle Hall and Koch, and in fact, I'm missing there also Lean. No, sorry, I do have Lean. So proof reconstruction in Lean is done on the internal format CVC5, and then in Isabelle and Koch is done on ALET. And what is this? It's a major effort, part of the effort that I mentioned, to increase the level of automation in interactive theorem provers by allowing them to send a sub-goal to an SMT solver, get the answer, and then get back a proof that they use to internally reconstruct the proof arguments so that the sub-goal in question can be proven internally, okay? So interactive theorem provers are skeptical provers. They will not accept the results from the outside, okay? But what we do essentially is to say, well, yes, the goal that you give me is valid. Here's a proof. And we have built internally in each of these systems a formalization of our proof system, as well as tactics that, based on the proof obtained from CVC5, they redo the proof internally in their native format. And this process requires a lot of effort and a lot of time. But in the process of doing this, because we had to introduce basically the logic of SMT-lib and all the rules of CVC5, we've proven formally in these tools the correctness of all the rules that we have actually encoded. All right, very well. I do have some results, but I will skip them because I'm out of time. These are also initial results that are already obsolete because they keep improving, and the results here describe basically the sort of overhead that you have improved production and compare various approaches. That is, using DRAT or not DRAT, using different solvers for the proof sketch. The overhead of proof production, elaboration, and checking versus just solving. This is all work that it's continually evolving because we are improving the tools as we go because we want to have very small overhead. All right, so to conclude, the last few years, we've been working on a framework for fine-grained proof reconstruction and, well, comprehensive proof generation, now available for SMT problems in general. I mean, the framework, of course, is specific on to CVC5, but a lot of the tooling around it could be used by other solvers, including the UNOIA language and the ethos checker. Working with the theory string has really been a milestone because of its complexity, and again, the importance of this theory to Amazon. They use this as in the Zelkova tool, if you know about Zelkova. Their proofs have to be generated very quickly and checked even faster. So it's really, right now, all of our implementation efforts have been focused on making that part very complete and efficient. Proofs are available through an API, so you don't have to go through text. And in fact, the integration in Lean is done that way. But then we have support for multiple textual formats, as I discussed. I told you about UNOIA that we have developed specifically for CVC5, but it's really general. It can be used by other SMT solvers or other theorem proving tools. We have put a lot of effort on integrating CVC5 in interactive theorem provers. This is, in a sense, the orthogonal goal, which is We want to improve the automation interaction with improvers. But in the process, what we've done is we've also ended up proving the correctness of all the entire proof system of CVC5 formally. Well, so we expect that the high quality and fully detailed proofs that CVC5 generates, will be enable a lot of future work and more applications. Why? Because, well, in addition, again, to allowing Formats tools to trust the results of an SMT solver, they also, can use proofs as artifact to mime a lot of information from. You can extract a lot of information from proofs. And so when you have fully detailed proofs, it can be really useful. One thing I want to conclude as a final note is that this process, we knew this in advance, but it was really confirmed that generating proofs, which is meant to be, a service for your users, is really good for you if you are a developer as well. This might be obvious to a lot of you, but I just want to go over it anyway because it's important. If you're forced to formalize the proof rules, then it really improves the code base because you really need to check that what you're doing in the code really corresponds to an inference that is formalized by a proof. So this uncovers existing issues, it forces modular design, clean code design, improves the robustness of the tool. We went through this process. We found a lot of bugs in CVC5 when we decided to add proof rules. And so proofs are valuable for debugging. In fact, we also had external users, have CVC5 generate a bogus proof, that is, they didn't check and report back to us. Because of the level of detail in the proof, then we can identify relatively easy the point in the, this humongous piece of code where the error was. And then, of course, proofs are integrations, are a gateway to integrations to other systems, as I discussed before. And finally, lots of information is in there. You can extract interpolants, you can extract unsack cores, and all sorts of goodies. So I'll stop here. Thanks a lot for your attention. And is there time for questions?
Okay. Moshe?
Comment and a question. The comment is you keep talking about the overhead of proof production. I think that's a bad attitude. Proof production should be part of solving. We should not think about solving without having. If I have a complex solver, what do I know? How can I? The whole point is to trust the result.
I absolutely agree with you. Absolutely agree with you.
So we should just change terminology.
But let me answer that comment before you ask the question. This argument will not make you any friends at Amazon. Okay? I don't care.
I've already lost my friends in Amazon.
I don't care. They go like, this is too slow. Okay? The moment you introduce proof production, then all their regressions fail. Okay? So what they want is lazy proof generation. We do proof logging, and then later offline, the proof is generated and checked. You can't do this in line.
No, that's fine. And that's an argument about what is a practical way to generate proofs.
But it's important to design the system so you can do that.
I completely agree. But the point is we should just put in our mind now that solving means also proof production.
I cannot agree more with you.
Okay.
Just giving an answer without evidence for it, it's not useful anymore.
Yeah.
It was good before, but of course, this community has been doing this for a while, like in the competition.
But we just need to internalize this.
Yes,
We need to
all of us need to
rewire our brains. It was not there from the beginning.
Yes.
But now we saw the light. We're blind. Now we can see proof production is part of solving.
I would like to argue that it's not that we were stupid before. It was just hard to do. Now we have better ways of doing it.
Okay. Question.
Yes.
I didn't quite say, maybe I missed it. How do we know that the rewrite rules are trustworthy?
So the rewrite rules are specified formally, okay? Together with.
But are specified, but maybe the person who specified them made an error.
Absolutely. So that's why we have taken all of these rules and formalized them in, say, Lean, and proved them correct in Lean.
In Lean, okay.
Which is a huge effort because basically that requires not only to encode SMT lib's logic, the specific logic of SMT lib, but also all the theories that you're using,
Yes, yes.
right? Which means, big libraries, to be able to say, yes, this derivation step or this rewrite step is correct with respect to the semantics that we have. So yeah, we've done that. Not fully, we're not done, but it has to be manual, right? You can automate it only up to a point. At some point, you need a proof. Now, I have to say, there is a level of automations in the sense that, for instance, in Isabelle Hall is a good level of automation with respect to younger systems like Clean. Often the proof is found itself by Isabelle Hall. That is, we write the theorem corresponding to the rewrite, and Isabelle Hall will find it automatically, right? So it's not like we did everything manually. There's a lot of stuff that the tool has helped us with. But we have uncovered errors, either when we were writing the proof or when we realized it couldn't prove it. And it wasn't because, again, Isabelle was not smart enough. It was because the proof actually didn't hold. I mean, the rewrite didn't hold.
Okay. Oliver?
You are using a very complex system, and I wonder, could you just give a few comments on the level of trust? Or so I assume you are not fighting a hostile system where where the hardware, the software could be attacked. But one of course assumes so in the future our systems could be used as extreme safety and security concerns where terroristic attacks and all that. Perhaps a few comments.
Yes. So we're not solving that problem. What we're doing is, look, you don't need to trust this large and complex system. You need to trust this small proof checker. You could still attack the proof checker. The proof checker might still be wrong, but it's a lot simpler. And so you can imagine debugging it extensively or even trying to prove it formally. But the entire process will break, that is, the success of proof checking will break if there is an attack, before the proof checker. That is, if you corrupt CBC5 or you corrupt the proof and so on, it will not proof check. Now, if the corruption actually makes the proof check, that corruption happens to be meaningful or produce an alternative proof, right? So you don't worry about that. You only worry that the proof checker needs to give you the okay. So if you trust the proof checker, the entire rest of the system not be in the trusted core.
So although Moshe told us not to ask this question, but you flash the slides very quickly. If I just run the solver with proof generation, and then full proof verification of the elaborated proof formula. Could you say something about like the overheads you currently have?
Yes.
Like what order of magnitude are we talking about?
Now, where did it go? When we started with this overhead, so solving versus the entire process, which is quite high. This is already obsolete. So the overhead now is 3.5 times. That is, it takes 3.4 times more to do everything than to just solve.
So just solve from actually solving and generating the proof and
no, just solving.
Yeah, just solving compared to proof generation and also checking with this ethos thingy.
Yes, but the process is longer than that. Is proof logging, because proofs are generated lazily. Proof elaborations, which means full proof, and checking in this case in ethos. Okay, our proof checker.
And how far would you be from like a formally verified version of ethos? Or?
Well, I mean, we barely started with ethos, so it'll be a while to formally.
Okay.
But if those results, which again are not acceptable, give you also this breakdown, right? Solving, logging, elaboration. This should be ethos, and this is the situation where we use DRAP proofs. So together the checkers use 20% of the time, the total time. And there's quite a bit of time in logging, and elaboration is really the the thing where we can improve a lot, and we have, because again we went from 7 times to 3.4, and we're still improving. So we expect to bring the number down quite a bit.
We have time for one more question, please.
So I understand that the proofs are must, but the obligation to generate proofs, does it affect the power of rewriting in any way? I mean, what you can rewrite and what you cannot?
No, because we actually completely ignore the proof generation during rewriting. So maybe I didn't stress this enough because I think it is a cool thing that we're doing. The rewriter is really complex. It does its thing. So when the rewriter says, I go from this term T1 to T2, in the first approximation proof, it just says by rewriting, okay? So set of terms as a whole, you need to trust it. So what do? We have a completely separate process that matches that pair to the database of rewrite rules that we have and generates, it finds in there the rewrite rule that most closely justifies that rewrite, or sometimes the sequence of rewrite rules, okay? So that allows us not to touch the rewriter at all, which is extremely important because the rewriter is called constantly. And again, it's complicated. Doing proof logging in the rewriter will really kill performance. Does that answer your question?
Okay, so I think we can close and thank our speaker again, and we take other question offline.
Thank you.
Okay, so there's please. I'm supposed to be okay. So
So I get the
behalf
goodies.
of Saturday.
Yeah. Maybe a picture. Okay.
Oh, better not. This.
Can I have another one now? No, wait. Hold on. This way. No. Oh, I should open and show it. Yes. All right. Oh, wow, this is fantastic. Well, thank you very much. I know my wife would really like this. Thank you. Here. All right. Thank you.
The speakers for the next session and the chair, please stay back. Yeah, I got you. And does he have a ये मैं पुश करने को बोलूँ HDMI
पहले पहले साइड में जाके रख पहले प्रॉब्लम हो No, this is
Ok, ça fonctionne? Non. Does it work? IO center, lead road. Then, is it working? No?
Yes, I got your PPT.
What?
I got your PPT.
Oh, yeah, but that's too. Oh, that's
when
annoying.
you're putting it on with the
Hmm?
and
Okay, so
this should be
that's fine. It's going. Just okay. Hmm.
fine. This should turn it on and off.
That?
This
Yeah. All right. Pas précis, les fous. No, doesn't work. Okay.
To come this
Okay. Okay. If I don't see it, okay. Yeah.
Okay. So what will you be using?
Yeah. Okay. Hello, test. Hello.
At the end, you just press.
Okay.
Yeah,
Okay. Test, test. Yeah. Okay.
the volume at the end, but yeah.
सेशन में बोला है कि इसको खुद that is very good because इसका स्लाइड
Our own laptop, because we can't do keynote presentations. We can go for PDF. PDF. Yeah,
PDF.
This is PDF. This is PDF.
Oh, I can connect my own laptop.
Then let's do it. Air dongle, air dongle. Wireless HDMI. Yeah, yeah. Do we have all the slides? We are setting up the very first one. Rest two are all set up. The first one has been. Yeah, yeah, yeah. Yeah, yeah. Yeah, it'll be fun. बैटरी है चार्ज करने की जरूरत पड़ेगी? ठीक है चलो हाँ ये इसको डिटेक्ट कर मतलब ठीक है ये वो है पॉइंटर है.
No, but I think that's thinking that this is a keyboard.
No, not this.
But I think it's okay. Yeah. This is
This
yeah.
is mute, right?
This is
And
the
you need to
point.
join the meeting as well. Wait.
Yeah.
Cursor is not here. You have to bring your cursor here.
No, but cursor doesn't come.
Okay,
Presentation mode.
then you'll
Oh,
have
this is not
no.
like a laser point.
This
or
is not a
something.
laser point. Comes up here. Just move your cursor.
Oh, this is I think cursor.
हाँ नहीं इससे पहले मीटिंग ज्वाइन करनी है. Can you open a browser?
हाँ.
On the table.
No, but if I want. Or like this, like this. Oh, like yeah. Hello, hello. Yeah. Teams. Yeah, yeah. I think. Then
Okay,
continue on browser.
That should also. Audio test करना है जल्दी.
Yeah, I think. Hello. Yeah. I think it's fine. Yeah, yeah.
Recording.
Oh, camera is.
And let it be off.
Yeah. Oh, name. It's asking me. Hello.
How do you? No, the speaker.
You mean the audio? Oh, yeah. I think. Screen.
Hello. तू कुछ बोल.
Hello. This is the mic or this?
This is just backup in
Oh,
case.
okay, okay. Yeah.
And D&D. Do you want?
Oh, on the laptop, like.
At the top. With
Oh, control. Yeah. Yeah.
ये नहीं हो रहा है.
Oh,
मेरे लैपटॉप में देख रहे हैं क्या? दोनों लैपटॉप में देख.
no, this. I
Screen
think.
is not being shared.
Oh,
We share it. I think we stop.
oh.
Yeah.
Yeah.
Yeah. Hello. Hello. Okay. No, I had something. Yeah. Huh? Present. Okay. uh,
I already did, I think so. Okay, so